Good morning. So far we've developed the models that we are going to be using for circuit analysis. And now, basically now we are going to dive into the circuit analysis. And the first and perhaps the most important parameter when you think about integrated circuits is the concept of gain. And that concept really goes back to a notion of a device, right? And we kind of alluded to this before, that has a controlling terminal and a control terminal, right? So you control a parameter, let's say a current of another terminal under the right circumstances by controlling a voltage or current of another terminal. And this was in my opinion, it was a major breakthrough to recognize this concept, as simple as and as trivial as it may sound today. And I think actually the credit goes to Lee DeForest, who also invented vacuum tube, although the triode vacuum tube, which basically he didn't quite understand, I think, how it worked. They called it audion. But that was the basis of being able to provide meaningful amplification, not only amplification, but also cascadable amplification. And this is another thing, that if you don't have that separation between the input and output terminal, you may be able to get some amplification under certain circumstances, but it may not be cascadable. And that ability to cascade and put them back to back in series is an important parameter because it allows you to process the signal in stages, be it analog or even digital and all those things. So that concept really is the core to the concept of gain. And when we talk about amplifying stages, that's one of the things that we should keep in the back of our head, that it's that concept that matters. So what we are going to do today is that we are actually going to for you to get a sense of what is the commonality and what are the differences between these stages. I mean, we are going to be using BJTs and MOSFET in parallel. So we're going to be showing the parallel development of what it looks like for certain things in BJTs and MOSFETs. And there are other devices. You can use JFETs, we can use vacuum tubes, we can use all sorts of other things. And then we are not going to be able to show all of them in parallel. I don't think it's particularly useful to do multiple ones. But on the side, I will try to create a third column of what I like to call an arbitrary three-terminal device, or ATD. So we'll see if you had an arbitrary three-terminal device, what is common to that with some arbitrary characteristic. I mean, it's not entirely arbitrary. We'll talk about some of the general properties that we assume it has, but the exact relationship between the current and voltage, that functionality, is somewhat arbitrary. And we'll see what is common to all of these things and what is specific to particular stages. And the importance of this comes from the fact that, as we discussed before, we are using these as surrogates of these arbitrary three-terminal devices, or ATDs. But the devices of the future, 20 years from now, 30 years from now, the devices may behave very differently. Even today, the MOSFETs, some of the MOSFETs that we use are not really particularly the same in terms of the IV characteristic under certain circumstances as this ideal quadratic MOSFET that we talked about for a variety of reasons, because of the structure of the device or the velocity saturations and things of that sort, right? So the point to take away from all of this and subsequent discussion is that we'll use these as examples of how these techniques apply, and you will see that some of the specifics of the device will have significant implications in the way the circuit topologies are developed. The same way that, for example, the economics will have a significant implication on the way we implement these things. So the idea here is for you to have a sense of why we are doing it a certain way, and also have a sense of what are the other ways of doing it in case those parameters of that trade-off change, right? If we end up making circuits in a very different way 30 years from now, you understand what are the knobs that affect this trade-off, and you will be able to adjust your topologies and everything accordingly. So that's the idea. Okay. Any questions about that high level before we dive in? All right, so let's get in. So we'll do bipolar on one side and MOSFET in the middle, and then I'll try to fit them. So what we'll do, we'll kind of write some stuff on one whiteboard, on the third left, and then we'll switch to the next whiteboard, third left, and then we'll come back and fill up the middle left and middle third and the right third. Okay, so let's say, we allocate the left-hand side to BJT. And what do we know about BJTs? again, to refresh your memory, starting with the symbol, you have an NPN device that's shown like this, and a PNP device that's shown like this. The one with the arrow is always the emitter. And what you have here, the current direction of the current flow, this is IC, this is IE, and this is IB. And likewise here, this is IE, this is IB, and this is IC for a PNP. This is an NPN and PNP, so those are the basic things. Again, I'm going to just do the high level of the MOSFET and the arbitrary device here too. So let's say MOSFET. Again, the symbol for an NMOS and the symbol for an PMOS or PFET or NFET, and NFET. So let me just use a slightly different color code than for MOSFET. And the current flow, so this is, of course, the source, the drain, and the gate. So this is ID, this is IS, and if there is anything, it would be IG, and here would be IS, ID for PFET, and IG, shown that way. And since we are doing this, let's do our, what we call arbitrary three-terminal device, or ATD, arbitrary three-terminal device. And I made up a symbol for it. So this is our symbol for the N-type arbitrary three-terminal device, and this is the symbol for the P-type arbitrary three-terminal device, where we call this terminals 1, 2, and 3. 1, 2, and 3. 1, 2, and 3. And the current flow is I2, essentially, I1, and I3, and I1, I2, and I3. And you should probably be starting to see like we are going to develop them in parallel, essentially, so it's for you to get a sense for what the commonalities are. Now, let's go to the bipolar. Let's start with the BJT. So what is the fundamental, what's the first order behavior of the bipolar? What is the part that's particularly useful? We know that because of the potential barrier adjustment, it's a thermal device. You lower the potential barrier between the base and the emitter. And what happens is that more charge carriers, in the case of an NPN, it would be electrons. In the case of a PNP, it would be holes, flow from the emitter through the base. And once they're in the base, due to the random thermal movement mostly, and some other secondary effects, they make it to the collector. Once they're at the edge of the collector base, there's an electric field that absorbs them in, sucks them in, and they form the collector current. So that would be this flow. And of course, the flow of this is the opposite of the flow of the electrons, because electrons are negatively charged. But anyway, so what we know is that IC to first order is really IS, e to the VBE over VT. There is the early effect on top of that, which we may or may not want to write. I'm just going to put it here for completeness. So it's going to be VCE over VA. We have developed these expressions before. And we know VT here is KT over Q, which is roughly 25 or 26 millivolts at room temperature. Right? So the most important part of it is this exponential. So we can, for now, ignore that. And if you look at this, if you plot, that means that basically if you plot IC versus VCE, IC versus VBE, you have an exponential behavior. And this exponential behavior is captured by this. So that's the basic part of the transistor. And then there's a second part, which is this part, which is also captured by these curves. We've covered these before, so I'm just going to do this quickly. VCE versus IC versus VCE. So if you look at it for one given VBE, you have something that looks like that. And then for a different VBE, you will have a different thing. So this is VBE1, VBE2, VBE3. So these are different values of VBE. Here is when you are in saturation, when the base collector junction is forward biased, and here you are in the forward active region. And what you have here, if you get a little bit deeper into this thing, so there are these parameters, right? So we at any operation point, if you say I'm operating at this operation point, let's pick an operation point. What you have is that, so you can basically, if you have fluctuations here in voltage, it corresponds to fluctuations in the current. And the ratio of those things, again, we've done this before, so we're going to do it quickly. We define that as the GM. So the GM is really defined as DIC to dVBE. And the reason we show them with partial is that it's also a function of VCE, for example. So there's more than one variable here. So, okay, so that's what that is. And so that's the GM, so that's the slope of this line, is the GM. And you can see it's a function of the operation point, or so-called bias point, or quiescent point. These are all the different names for the same thing. So if you hear quiescent, I sub Q, or ICQ, or I bias, or I operation point, etc., IDC, all of these things mean the same thing. Now, and here you have these slopes. And what are these slopes? So if I ask you, what is this slope? What would you say? These slopes are really, at any operation point, these slopes are measures of what? I mean, how do you define the slope? Right? It's DIC to VCE, right? So it's DIC dVCE. And we've defined this before, and this is basically defined as RO, the output resistance, or more accurately, 1 over RO. So this is, RO is 1 over that. So this slope is really 1 over RO. Because this is I over V, not V over I. So it's a conductance. It's GO, if you will. So this is the basic property of the transistor, right? And it's also because of this exponential behavior, you can see that the spacing of this, for equally spaced VBE, this spacing is increasing. So these are not equally spaced for equally spaced VBE because of this exponential behavior. So this is really capturing this part, and this is really capturing this part. I might as well just rewrite these with these, show them with these colors. So you can say exponential of VBE over VT and 1 plus VCE over VA, which is the early voltage. Now, in terms of the parameters, the size of the parameter, we talked about this. So GM, when you do the calculation, you can show it is basically IC over VT when you do that derivative. So it's defined by the collector current. And for example, for 1 milliamp, this is 25 millivolts, it's 40 millisiemens. That's a good number to remember. So at 1 milliamp, it's 40 millisiemens. And RO is also a function of VA, the early voltage, and IC. And let's say if you have a VA of 50 or 100 or something like that, it can be anywhere between like few tens to 100 for a typical bipolar transistor. You're looking at, and at 1 milliamp, let's say if this were 100, you will get 100 kilo ohms. So just to get a sense, remember, this is on the order of 100 kilo ohms. GM, which is 1 over RM, by the way, and we use RM from time to time, actually quite a lot, is going to be 25 ohms, right, at 1 milliamp. So at 1 milliamp, you're talking about an RM that's about a few tens of ohms. You're talking about an RO which is in the tens to hundreds of kilo ohms at 1 milliamp. And you can see they both scale together, right? Because they're both dependent on IC. They're both inversely proportional. RM and RO are inversely proportional to IC. So the ratio, obviously, as you can see, is the VA over VT, which is independent of the collector current. And we'll see that this ratio is very important as we do our development. It's actually a fundamental, something that tells you how good a transistor is in certain ways. And we'll see why in a second. Okay, so that's the very basic behavior of the BJT, right? And we'll come back to MOSFET and our arbitrary device later. So let's see what this does in terms of designing an amplifier. So we still haven't designed an amplifier yet. We haven't designed our first amplifier. So we are trying to make an amplifier. We have a device that under the right set of operation, under the right region, in the right region of operation, has a dependence on an exponential dependence of the collector current on the base emitter voltage, right? Let's say, for the sake of argument, we want to make a voltage amplifier. Now, there are different kinds of amplifier. You can have voltage amplifier, you can have current amplifiers, you can have trans-resistance amplifier, or more generally trans-impedance amplifier, or trans-conductance amplifier, depending on the choice of the input and output, whether it's a current or voltage. And we said this, and we will repeat this. It's really a question of what the input and output impedances are. Whether or not something is a voltage amplifier or a current amplifier classified is somewhat of an abstraction that can be helpful to think about stuff, but really there is no differentiation. There's no dividing line. It's a continuum of the input impedances and output impedances. And some regions of this continuum we call voltage amplifiers, and sometimes somewhat rather arbitrarily, and some regions of it is called current amplifiers, again arbitrarily, right? So here's the thing to think about. We have this device, we want to make a voltage amp, meaning that we want to create an output that's a voltage. That's an amplified version of the fluctuations at the input. We have a device that converts the voltage fluctuations to current. So what else do we need? So we have something that takes the voltage fluctuations. So we have voltage fluctuations, let's say V in, and it converted to a current, let's say V in. Or if you're talking about the fluctuations, V in, lowercase, to some fluctuations in the current, in this case the collector current, IC. Now we want to convert a fluctuation in the current to a voltage again, right? So we are going to, from this fluctuations in the current to some voltage, which is our output voltage. What do we need? Well, essentially, any two-terminal device does that, right? You put current, at least something that's a general resistor. Now, the general resistor doesn't have to be linear, and it can have any kind of behavior. But you are looking at a general nonlinear resistor that converts this current to a voltage. And then the question is that what do we use? What kind of resistors do we use? What kind of load do we use? And then the choice of load leads to a whole bunch of different topologies. So a lot of different topologies that we'll discuss are really question of what choice of this load do we use. And some of that is dictated by the requirements of gain and such. Some of them are dictated by the requirement to use the minimum number of passives and maximum number of actives if you're on chip, and things of that sort. Right? So a lot of our discussions would go into this choice of this load. But that's where it's coming from. So we have to choose the load. Choose a load. Something to connect it, something to convert the current to the voltage. Okay, so what is the simplest kind of load? But that's why we call it load, basically because it converts this, it's loading the output. And what should we use first? What is the simplest kind of device, a two-terminal resistor that we can use?
I was just going to say a purely resistive.
A purely resistive load, or a linear resistor, or a typical standard resistor, right? So that's the simplest thing. So it appears that if we were to use a transistor, so let's say we want to kind of do this. So would this be a good load? Let's say RC. So this would be our V in and V out, if we were to use it this way. If this was our entire circuitry. In other words, I mean, we show a ground like that, which basically means that there is a potential here applied. But let's go to this shorthand notation, and if you had questions about it at any time, feel free to ask me. Okay? So is this a good amplifier? Is this an amplifier? Does it satisfy? So this is the entire circuit. So I'm taking a transistor and a resistor, and I'm applying some voltage here, and I'm expecting some amplified output here. Would I see an amplified output? This case? No. A lot of people are shaking their heads. Okay, so that's good. So why? Yes, Nikhil.
You can have it in the forward active region because not the base emitter and base collector wouldn't both be, or the base collector wouldn't be.
Right. I mean, not in the forward active region. That's the response, because both base collector and both base emitter, so if this is at a higher potential, they are at the same potential. So if this is forward bias, this is going to be forward bias too, because this is connected to ground, right? So first of all, I'm not in the forward active region. This transistor isn't going to be in saturation, the way I've drawn it. And there was another argument that you could have given me, even simpler, more physical argument. That was a good argument, by the way, don't take me wrong. So another argument, even a simpler, more physical argument, that why this would not be an amplifier. The way I've drawn it, yes. Where's the power coming from? Right? There's no source of power unless there's some magic source of energy inside this thing that you can tap into. There is a source of energy in there, which is the thermal energy, but unfortunately, thermodynamically, it is a very high entropy, the highest entropy source, so it's not possible to extract a lot of useful work out of it from a thermodynamic perspective. But anyway, so going back to this question, so this is not going to work because the transistor is not in the forward active region. So what do we need for this transistor to be in the forward active region? We need this junction to be reverse biased. Or in other words, we know that for that to happen, that this voltage across the collector emitter needs to exceed 0.1 or 0.2, or what we call the VSAT, capital VSAT, right? So how do we achieve that? First of all, these two responses, right, the fact that we don't have a source of energy and all those things, and the fact that we are not in the forward active region, we are in saturation, both lead to the same thing. You need an external power supply. Again, we are starting from very basic principles, and we're going to build up. So how do we apply it? So there needs to be some voltage source. There needs to be some DC power source, either a battery or a DC source or something like that. So, and that needs to take this node and pull it up. And that can happen through a resistor. So if you put some VCC here, and this is your RC, now, at least under the right set of circumstances, you have a chance of this voltage being higher than 0.1 or 0.2. So this VCC is assumed to be higher than ground in this case. And as such is drawn at a higher level in the schematic. Okay? So now we have a shot, because at least we can have, under the right set of inputs and parameters and all those things, you can have a point that this voltage is higher, and this resistor is also still seeing the fluctuations, because if you apply fluctuation here in this voltage, this would result in a fluctuation in this current, right? So you can have this V in fluctuations of V in. So this V in also needs to have a DC part, so which we haven't shown, right? So what we really are talking about is that there's a V in, the fluctuation part, plus some DC part, some VBE, or you can call it capital V in. So that's basically the DC part to maintain this, but also we have to maintain this forward bias, right? Because if you just take a sine wave, for example, and if you didn't have this VB, right, and apply a sine wave to the input, so what's going to happen? The transistor is going to be off for whenever the sine wave is below 0.6, 0.5 volts, so this is 0.6. So it's off for all of this stuff. So what's going to happen is that you will see some fluctuation around here and nothing over there, or very little at least. This is called biasing, and we'll talk about this more extensively, and we'll talk about it in multiple stages. We'll go and become more and more sophisticated with this biasing of the stages. Which is an important part of the thing. And that's the part that when you design, actually a lot of people have most trouble with. When we get to our project, for example, that's one of the things, that first things that you need to get right. You need to get the transistor biased properly. So, but anyway, so it's not too complicated, but we need to also kind of be mindful and cognizant of it. Okay, so here's what that is, right? So this VBE fluctuations corresponds to this IC fluctuations. So these lowercase ones are fluctuations, right? Changes, perturbations, if you will. And this basically now going through the resistor, so it would induce a fluctuation in this voltage. This voltage will have some DC level around which you will have some fluctuations of V out. So there's a DC total response. There's a total response, which is the combination of the two. There's a DC part of this thing, and then there's an AC part, the red part. And we need to understand these separately, and that was the basis for the small signal model, and we will see it more. But so let's see. Let's write the expression. So if I have a circuit like this, even from a purely DC perspective, so I'm going to write the entire characteristic. What is this total IC? So this is capital I, lowercase c, which basically means the combination of everything, all of the entire current. Well, we know what it is. It's the exponential, right? So what is this V out in terms of this IC? Well, we know this voltage is VCC, right? And we know the current through this resistor is what? IC. So this is VCC minus RC IC. Right? This is the voltage drop across the resistor. This is this voltage, so this voltage is going to be that difference. So that is what we call the load characteristic line. And we'll see why we call it that in a few seconds. But what happens is that, so that's what it is. But we know we have an expression for IC in terms of our aggregate Vin, right? Because that's the behavior of the transistor. If you're in the forward active region, then this is basically VCC minus RC IS e to the Vin over Vt. Because now VBE is the entirety of Vin. You can call this, if you, I think probably in this case it would make sense to call it Vin. So this total thing, this whole thing is capital V lowercase n, which basically means that the whole thing in our notation. Okay? So that's what that is. So you have a V in, V out characteristic right there. And you can see it's highly nonlinear, right? If we plot this V in, V out characteristic, so we call it the characteristic function. So what we have here is that, so what do we get? If Vin is 0, which means that it's entirely 0, what is the transistor? What's the current in the transistor? Current is 0, right? Right? So, or very close to 0, it's going to be IS according to this. There's the -1 which we've dropped, but it's essentially going to be 0. And so we have no current flowing. When there's no current flowing through the resistor, what is this voltage? This V out? This VCC, right? And as you increase it, you gradually have the exponential coming in and reducing this voltage. This term kicks in, and when would it continue forever? No, something happens, right? Something changes at some point. What is that? Once you get to a level which is like 0.1, 0.2 volts, the VSAT, then the transistor enters saturation. This junction is forward biased. Therefore, the actual characteristic would look like that. It's kind of a little bit of a more graceful transition, but regardless, it's something like that. So this is your V in, V out characteristic. And you can see it's highly nonlinear because they are dealing with an exponential. You are getting the slope of the exponential, which is good, which basically means that you have high gain in principle. You can have high gain, depending on what the values of the other parameters are, as we'll see. So that's basically the V in, V out characteristic of this thing. And it's an exponential. I should draw it even a little bit sharper than that, the way I drew it. I mean, of course, it depends on the parameters, as I said, but just something like that. Okay. Is this good? Is this bad? What do you think? What are your observations about this? And we'll talk about this, what is a good gain characteristic, what's a bad, what do we mean by good and bad in different conditions and things of that sort. Any thoughts on this? Any observations? Anything that you see that you like or dislike about this? One thing is that inverting. So that's one observation, right? Because when the input goes up, the output goes down. So it's an inverting gain stage. That's a good observation in that sense. So they go in opposite directions. So that's good. It's highly nonlinear. Okay. And we'll see why that matters later on. And it has a limited range, as it will, as it should. I mean, basically, just if you have something with high slope, it cannot have a very large range with a given amount of supplies. So you can't have a very high range of operation and a very high gain if you have limited supplies. That's very fundamental. I mean, you can't have a very steep line that goes very long range horizontally at the input without having a long range vertically. It's basic fact of math. Right? So, okay, so that's what it is. So what is the gain? What is the gain of this thing? How do we define gain? How should we define gain? Do you agree that a good definition for gain is perhaps saying, and we show this as voltage gain, which would be the ratio of V out over V in is going to be, by definition almost, is dV out, capital dV out, versus dV in. Right? It's a derivative, the slope of this transfer function. So what is the derivative of this thing? Well, the derivative of the first term is 0. It's a supply. Right? Now, this derivative being 0 is important. Another way to think about this is that all DC supplies, and listen to this carefully, because we see this more frequently than we would like to in your homework problems, that not this year so far, but just like I'm saying that generally, that any DC supply from an AC perspective, from a small signal perspective, from an incremental perturbation perspective is what? It's a derivative of the DC. 0. So now, depending on what kind of source you have, that 0 may mean a different thing. If you have a voltage source, that 0 means a short circuit. Short circuit to wherever it's connected. If it's connected while the other terminal is connected to ground, it becomes ground. If it's a current source, it is an open circuit, right? So it is basically that. So this derivative being 0 means that those independent sources in AC, if there's a DC independent source like a battery or current source and things of that sort, they become 0. And whatever that 0 means depends on the nature of the source. But anyway, so let's do the derivative. So what is the derivative of this thing? It's negative RC IS. The derivative of this guy, the derivative of x exponential gives you a 1 over Vt exponential of V in over Vt. Right? What is this quantity? Do you recognize it? This is the IC itself, right? So I can write it as negative RC IC over Vt. And this quantity should be recognizable too. Now, look up there in red. That's GM. So it's negative GMRC according to this calculation. So it says the gain is, the negative sign comes from the fact that it's inverting. That indicates the fact that it's an inverting amplifier. So the gain is negative GMRC according to this calculation. And it's basically coming from this derivative. There's nothing magical or out of the ordinary really about that. So that's what the gain is. Now, also, so that's one viewpoint, right? So you can take this generally nonlinear transfer function and differentiate it and get this. There are two ways to do this. In general, this is true about when you do calculations in all fields, including electrical engineering and including circuit design, is that if you're going to make, you can do carry the full analysis or some level of more complex analysis through and then do an approximation at the end, or make that approximation up front and carry through a much simpler calculation. And if you have a choice, if your choice is really as simple as what I just described, I would opt for the latter. I will do the second one. Because if you're going to make that approximation anyway, you might as well make it up front, make your calculation simpler so you get more insight. So the objective here is not try to replicate the exact to the third significant digit numbers in your design, because you will not be able to do that regardless, because these models are not that accurate anyway. We've seen how many approximation has already gone into it. So the same, and we applied this principle when we were looking at, for example, diode and BJTs, right? PN junction and BJTs. What we were looking at, we could have used the full Fermi-Dirac distribution and this and that, and then carry a full expression and then eventually simplify it to show it's an exponential for the most part. Or we can say, well, you know what? If it's more than 3 kT, it's going to be basically Boltzmann distribution is sufficient. We can use that and get our expressions much quicker. We are going to do the similar thing here to the extent that we can. So this is, again, the long way around. So what is the short way around? The short way around is to think about this and say, well, okay, if that's my stage, I can use, we have already developed a small signal model. And we can just directly apply the small signal model, which would be equivalent of doing this, without doing it explicitly every time and without writing those expressions. So what does the small signal model look like? So we had two models which were equivalent, the pi model and t model. And here's the hard and fast rule about when to use t model and when to use pi model. I mean, it's not a, well, it's a rule of thumb. My suggestion, okay? You can use whatever you want. So as far as I'm concerned, it's perfectly fine. Whatever you, if you use either one of them, you will arrive at the correct result if you use them correctly, because they're equivalent. You should arrive at the correct result. But here's, I think, what makes your life easier. If there is if your source or your emitter is connected to a fixed potential, pi model usually is more helpful. If your source or your emitter or terminal 1 in the arbitrary device is not connected to a fixed potential, is connected to a resistor or something like that, where that its terminal can move, almost like 99% of the time, it's easier to use the T model. So again, I did not justify this yet fully. We'll see this in practice. And since it's a rule of thumb, really doesn't need a full justification, because it doesn't have a full justification. We talked about why people initially were doing the T model and then moved to pi model. There was some historical and not probably completely justifiable reasons. But anyway, so this case is actually one of those cases where the emitter, in this case, is connected to ground. Another terminology for that is that you have a non-degenerate emitter. Because when you put a resistor in the emitter, we call it an emitter degeneration. That's the terminology that's used. So in this case, we can use the pi model. So what does the pi model look like? So now we are reading the small signal domain. So what does my input look like of these two sources? If I'm in the small signal domain, what would this become? Short circuit, this black one. This one is my fluctuation. This stays, right? So I am left with the small signal model, which is, so this is Vn. Now, what does my small signal model look like, the pi model? We have an R pi. We developed this before. So you have an R pi. And this voltage, we call this V pi. So right now, we are going to deal only with the low frequency components. We are not going to worry about the capacitors yet. We'll worry about them later. And we'll spend a fair amount of time about what the frequency behavior of the things are, but not yet. And then you have the transistor, the good part of the transistor, the GMV pi. And then you have, in general, you have an RO. And then now, this is the output. This is the collector. So this is the base. This is the collector, and this is the emitter, which is now connected to ground. So I could draw it this way, or I could draw it like this. They're the same thing. So I'm going to simplify it and draw it the way I just did initially. And then what do you have? You have an RC. Now, what's the other end of the RC connected to? Let's look at it. It's connected to what? What is this when I draw this line? What does that mean? We talked about it. We call it rails and all those things. Again, the terminologies. What is this? What in physical manifestation of this thing? What is it? Some fixed high potential, like a battery or a fixed supply, DC supply. So and as such, it's like this one. And therefore, should be what? A short circuit to where? To ground, because the other terminal of it is a ground. So that's why this is also ground. From an AC perspective, from a small signal perspective. AC and when I say AC's perspective, it's synonymous with saying it's small signal. Okay, so that's the equivalent model, the pi model. Many of you have already seen this model. And then the question is, what is the calculation of, what is the gain? So we can do that, right? So if this is Vn, V pi is going to be Vn, obviously. It's the same voltage. So this is going to be GmVn. So you have a current of GmVn being pulled out of this parallel combination of these two resistors. So what is this voltage going to be, which is V out, really? What is that voltage going to be? Negative GM times RO parallel with RC, right? Because that's the parallel combination. So we can see that VO, V out, is going to be negative because, and it's negative because it's being pulled, the current is being pulled out of it. Negative GM RC parallel RO V in. And therefore AV, the voltage gate, which by definition is V out over V in, is going to be negative GM RC parallel RO. So is this the same result as this? Well, not exactly, right? It doesn't look exactly the same. There's the second term, RO, which wasn't in there. Why wasn't it in there to begin with? What did we approximate out that led to this? Well, we remember our friend here, right? The early effect, this blue one. We did not include that, and therefore we didn't see its effect. Had we included that, we would have seen its effect. Because that would have been a more interesting equation, because then it would have been 1 plus V out, because VCE is going to be V out, right? So it's an equation, then you have to solve this for V out. So this would have been 1 plus V out over V in. So you have an equation that you need to solve. You will have exponentials on both sides. You can take derivatives and go through a lot of like fun algebra, and then a couple lines, not really a lot. But and then you will arrive at this result. So this is a more accurate result. And it makes sense because really what you're assuming here is that if you want, what do I need to do to VA to make this term disappear, this blue term disappear? What should VA be for it not to matter? Infinity, right? So if VA is infinity, what is RO? Infinity. If RO is infinity, what is the parallel combination of infinity with finite? Finite, the finite, the same finite, right? Exactly. So it would be RC. So it would reduce to that under the same assumptions. So, but this is a more general result, which you can see we got with less effort, particularly if you were to do that other part of the early effect in this, than that. So you make the approximation first as opposed to last, if you're going to make it anyway. Okay, so that's for that. So, and then the question is, so now one of the interesting key questions about this thing is that, so how high can this go? Let's say you will see it will appear that we are on this in the next, like several lectures. You will see that it appears that we are on this insatiable quest for gain. Right? You will see that we try to do everything we can to get more and more gain out of a single stage, or as few stages as possible. And by the way, why is that? What is the reason for that? We haven't really formally treated it yet, but it's important for us. I don't want to keep you in suspense. So just like it's important to know and think about why we are doing this if we are doing something. And when we get to it, we'll see that how it's useful to us, really, in more details. But why? Why do we want so much gain? You will see that you say, okay, we are getting a gain of 1,000 out of this one, and we are trying to get a gain of 1,000,000. And so, why? What are we trying to do with this all this gain? Yeah.
If you put together a feedback amplifier with infinite gain, you can control the gain with.
Right. It really goes back to feedback, right? The response is that you will see that the currency that you have when you are using a feedback, the real currency that you're spending is gain. And the more gain you have, the more you can make your feedback system to behave the way you want it, closer to an idealized system that you're trying to design. So that is why we are going to be on this insatiable drive, seemingly insatiable drive to get more and more gain. How can we increase the gain, right? It's not pure madness, just only partial. Okay, so here's the thing. So let's start with this and see what is the maximum gain we can get and how can we get it. But to do that, also we need to really look back at this picture a little bit more in more details. So one of the things that we need to do, we can go back to this picture. Let's go here. When we were talking about the large signal, And again, we will see this question addressed several different ways. So we'll try to address it several different ways. I'm trying to leave room for MOSFETs. So that's why I'm trying to cram everything here. So we had these other curves, right? Actually, we already have them. There's no point in redrawing them. So let's go back to them. So we have these IC versus VCE curves, right? And now we define this purple equation, if you remember a few minutes ago, that relates V out to V in. That's for the transistor. But we had a second equation, which is somewhere to be found. Which is, yeah, sorry, it was right there. So it was right in front of my eyes. It's this equation. This relates the IC versus V out. But remember, what is V out? How is V out related to VCE of the transistor in this stage? The collector emitter voltage of this transistor is V out, right? It's this voltage. That's by definition the large signal, the full nonlinear V out. So this defines what in this plane, in this picture, this purple equation. How can it be visualized? Can you? Because this VCE is V out, right? This is a line, right? We call it the load line because this was the equation describing the load. So what is this? Where is this line going through? Well, if you set IC to 0, V out is VCC. So one point on this line is VCC. If you set V out to 0, it's going to be VCC over IC is going to be VCC over RC. So another point in this thing is VCC over RC. So it's a line connecting, straight line connecting these 2 points. And why is it a straight line? Because this is a linear resistor. The choice of our load determines the shape and properties of this load line. And as you can see, for different kind of loads, we have different load lines. So now what's happening really, this is VBE is V in. So this is really your V in, right? This is V in. V in 1, V in 2, V in 3. So as you change V in, as you increase that, what's happening is that your operation point, your V out, which is this point, the x-axis, as you increase V in, you can see it moves from right to left, which because the operation point is the intercept point of the appropriate black curve, which is the transistor characteristic, and the purple, right? So as you increase V in, this voltage starts dropping, which is exactly this behavior. This behavior, right? So there shouldn't be any surprises here. So that's how it behaves. So now the question is that if I want to get more gain, so let's look at it from several different perspectives. We'll start with the harder one this time, not harder, but less obvious one this time, and then we'll see where it takes us. So from this picture, what do I need to do to get more gain? What is gain? Gain is how much fluctuation how much change do I get in this x-axis, the location of this intercept point on the x-axis, with fluctuation variations of the V in, right? Moving from one of these black curves to the next one. So how do I get more gain? What do I need to do? Or let me ask another question before we even get to that. Where do I get, out of these 3 points, where do I get more fluctuation on the x-axis for same fluctuation in the V in? This point, or this point? The one on the left, the one in the middle, or the one on the right? Where do you think we are getting more bang for our buck? Or we are getting more response? More fluctuations in the x-axis for the same fluctuation in the y-axis. The one on the right, this one? Or the one on the left, or the one in the middle?
The one on the right.
The one on the right. Why?
Because it has a lesser slope, so it takes more movement in the x-axis.
Okay. So, but how about this? Think about okay. So maybe I should have re-emphasized something that I said that earlier, kind of in a sense that you remember I said these are not equally spaced, right? The same fluctuation in V in would correspond to a switching from this line to that line here, or this line to that line, from this line to that line, and from this line to that line. right? It appears that I am getting more on this side than that side because of that. And again, that if you look at it, it's kind of consistent with this picture. Where do you have the largest slope? Here or there? Right? This here, right? Which corresponds to here. Right before you get into saturation, because once you start getting to saturation, the slope drops and you're right. I mean, you have much less. But if you are not in saturation, still, you get more gain here than there because of that, because of the spacing, the change in the spacing, because the exponential is increasing. So that's fine. So that's one way, again, to think about it. This is like a large signal perspective of this, which is useful. But if I wanted to increase this gain, wherever it is, let's say in the middle or someplace, what do I need to do is there something I can do? Because a transistor is a transistor, right? I mean, let's assume that you're given a transistor. For a given transistor, what are you going to be able to do to make it have more gain? What do you need to do to the slope of this line, this purple line? Make it less steep or more steep? Less steep, right? How do you make it less steep? You make RC what? Larger, right? As you make RC larger, this load line becomes shallower, like that. And if I make the RC larger and larger, it becomes shallower and shallower. So apparently, I get more gain, because now I have two things that are almost aligned. There's a problem with this, obviously, which we'll have to solve. We'll solve later. But what's the problem with this? If I want to take this to the limit, what would happen? Well, the limit is down here, right? What is my collector current in that case? Zero. So there's no current flowing in the device. Now you may say, well, I want to make it very, very small. It may not be zero, but it may be very small. Yes, you can do that. But a very, very small current, as we'll see later on, would correspond to very, very limited ability to drive anything. Especially if you have a capacitor, it would take a really, really long time to charge and discharge that capacitor when we get to it. So now while we're in this subject, and we'll come back to this, let me ask you this question. If you could draw any line anywhere or any shape, what would you draw to make this have a higher gain? What is the shape of the line? Any line, anywhere you could draw. To forget about how we implement it physically, we'll talk about that, or whether or not it's realizable or not. What is the shape of the line that would give you the most gain? Okay, so what is it? Anyone? Say again? So one proposal is a horizontal line, but that's not at zero, right? A horizontal line that looks like that. That's one thing. And that has a name in circuit theory. What is the component that generates a horizontal line? What is the component whose current is independent of its voltage? It's a fixed value, no matter what its voltage is. It's an ideal current source. So it sounds like that would be the thing. But is that the best line? Can you think of something that's even better than that? Let's say you could do anything. You could draw any arbitrary line. What is the line that would give you the most gain? Yes?
A line with a slope of 1 over R0.
One with a slope of, oh, you mean, okay. You mean this? Okay, so the suggestion here, the other suggestion, let me see if I can find another color here, is maybe, how about this line? A line with this slope. First of all, let's talk about this. What do you think? Do you think this is a good line? Do you think this line would give you more gain? I actually agree with David. This line is a really good line because the slightest fluctuation makes the output jump from here to there. It's just barely there, right? I mean, right on top of it, right? The slightest fluctuation, a slight shift from one of these black curves to just one right next to it, we are not showing all of them, just showing some representative ones, right? The slightest change would just make the output jump from here to there, instantaneously. So in fact, I would argue that one of these black lines, if you could actually replicate it as a load line, would be perfect. If you were kind of like sitting right on top of that line, that would be ideal, because an infinitesimal change in a VN would produce a finite and potentially large output, change in the output, which basically means an infinite gain. Right? What's the problem with this line, with this like light, faint green line? What is it? What is the problem with that line? I mean, can we make that line? Can we not? If we do, what happens? Things of that sort. So those are interesting discussions. We'll talk about things like that too also. But let's do a preview. Yeah.
I mean, it would necessitate a negative resistance.
It would necessitate a negative resistance, right? Because remember, this slope is the resistance in the load line because it's referenced to the VCC. So it's the VCC minus that. So a line with a positive slope would correspond to a negative resistance. Now, obviously, you can't go to the stockroom and buy a negative resistance. There's no, I mean, the component values start from positive values, or at best it's close to 0, right? They don't have a component of -1, -2, -3, -4, -5, right? But you can make circuitry that actually behave that way. Yes, Noel?
Is the output voltage like defined? Because for a particular input voltage, could it be any?
So it's a good question. So is the output voltage defined? Because if this line is exactly overlapping with it, then it's not defined, right? So let's start. It's really a limit, if you think about it in terms of limits, mathematical limits, right? So think about it. Instead of having that exact line sitting right on top of it, think about something that's slightly shallower, right? And sits like that. We've abused this black line so much that we can't even see it. So let me just redraw it. Are you okay with that line? That's still a negative resistance line, right? So now so if I have a tiny fluctuation, I have to jump from the curve that crosses here to the curve that crosses here to go across this, almost all of this range. So now you can see as I bring this green line closer and closer to the black line, this in terms of slope, the required change in the input to produce this large output range becomes smaller. And in the limit, that required change is 0, which is when you said, is it defined because it's all on top of it, basically means that it is an infinitesimal change in the input would produce a large output. But it's a good that you pay. It's a very good thing that you're paying attention to these nuances. Did I answer your question? Okay. Any other questions? So, but you can see, so if you could make something that was a negative resistance, then you can actually get even better than that. And the interesting question arises that what happens if you let this slope go beyond the slope of the black line? What do you think will happen? All right, think about it. We'll come back to that later, much later. But anyway, so, okay, but if you can't, let's say with the components that you have, or presumably have, so the best you can hope for is like a slope of 0. I mean, and then you see how to make these things, and you will see 2 problem sets that would actually talk about that and things of that sort. But anyway, okay, so going back to this conversation, so it seems that our gain is really achieved when RC is maximum. And this is also clear from here, right? The maximum RC you can have, according to this picture, is what? Is infinity, if you don't want to make it go into the negative resistance realm, right? And if you have infinity, what's the maximum gain you can get? So what would this parallel combination become? So AV max is going to be what? negative GM, or yeah, if you look at the absolute value of it, GM RO. And what is GM RO? Well, we know what it is in terms of collector current, right? So GM is IC over VT, and RO is VA over IC. And these guys conveniently cancel, so you're left with VA over VT, which doesn't depend on the operation point. We said VA is few tens to 100, maybe low hundreds to several high tens. So let's say 100. And if this is room temperature, this is 25 millivolts. So what are we looking at? I'm sorry, 25 millivolts, yes. That's 100 over 25 millivolts. Oh, did I miss something? Yeah, no, 100 over 25 millivolts. What is 100 over 25 millivolts? It's 100 times 40. 4,000. It's in thousands, right? I mean, high hundreds to few thousands. So let's say in the range of thousands. So that's, and of course, this changes from one transistor to another, right? So this is somewhat of an intrinsic property of a transistor. You can say, okay, you know, if you're given a transistor to design with, one of the things that you should calculate first, if something you're designing is relevant, it has relevance to, gain has relevance to it, you should first calculate what's its VA, and I calculate what's the maximum intrinsic gain of this transistor. And then that gives you a sense of what you can or cannot do with what level of sophistication and complexity. And then again, there are lots of things you can do if you're willing to make it sufficiently complex and pay the price for it. But yeah, so that's what we call the maximum intrinsic gain of the transistor. And we know VA dependent, for example, dependent on the thickness of the base and the doping constant. We adjusted the doping concentration of the base and collector relatively to make sure that most of the depletion region falls in the collector side. So all of that good stuff that we talked about plays a role in this. Okay, so that's for that. A quick thing, so let's see if we haven't missed anything on this front. There was one thing I want to talk about. Okay, now in this picture, can we also see that? Let's see. Let's say we use that orange line, that flat line. You can see that the fluctuation, the change from one black curve to another black curve, this deviation, right? This delta IC is what is simply GM delta Vn, right? Or if you want to write it even more in terms of our notation, we can say GM lowercase vn, which is the fluctuations, is IC, the fluctuation in IC. And then that fluctuation needs to be converted to fluctuations in V out. What is the conversion factor? It's RO, right? Because you're moving up and down in this, and you are trying to convert it to left and right. So it will be 1 over slope of this thing, which would be RO. So VO would be IC RO for this flat line. And therefore, you can see that the variation, the gain, the VO over Vn is going to be GMRO. So that's also consistent with this. All right? So that's one picture for the bipolar transistor. Any questions on this? No? All right. Let's take a break and come back to do the MOS.